ASEG webinar series, which will be presented by Dr. Ehsan Farahbakhsh from the University of Sydney. So just a few housekeeping slides before we get going. So the ASEG Society acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize their continuing connection to these lands, water and culture, and pay our respects to their elders past and present. So a thank you to our corporate members, which are displayed on the screen here. And also a thank you to our branch sponsors as well for making these events possible and for continuing to support the society. So just a bit of housekeeping during the presentation. So for any questions that you may have, please use the Q&A box or the Q&A icon, which is at the top of the screen that you should be able to see. And then we'll go through all of these at the end of the presentation. So yeah, just another mention about memberships. So for those of you who are not already members and are considering this, there are many benefits to membership, including free access to the monthly magazine called Preview and to the Journal of Exploration Geophysics. There is reduced entry fees to AGC conferences. So the next AGC conference is in Brisbane in March 2023. There is also access to job advertisements posted on the ASEG website, free entry to regular technical events in your state, such as this one here, where we have pizza and sometimes even free drinks, so it's definitely worth it. There's things like annual wine offers, social events, and it's a great place to meet new people, make connections, and increase your professional network. And there are also every now and again scholarships available for students, which can be applied for by members. And there's free membership for students and half-price membership for retirees and recent graduates. And yeah, please keep in touch. We have monthly email newsletters, and we're also present on all of the social media outlets, including Facebook, Twitter, LinkedIn, and YouTube, where we post recordings of each state branch's technical presentations. So great. Now just to introduce the speaker today, Dr. Ehsan Farahbakhsh. Is your presentation now? You can open it up. This one here. This one. Okay. So I'll just read so just to introduce Ehsan. So Dr. Ehsan Farahbakhsh is a research associate in the Earthbite group in the School of Geosciences at the University of Sydney. He holds a PhD degree in mining engineering and mineral exploration from Tehran Polytechnic. Along with his research activities, he has been involved in several projects as an exploration geologist and spatial data analyst for the exploration industry. And he primarily provided prospectivity maps of various ore deposit systems from the regional to deposit scale. His research interests are multidimensional, mineral prospectivity modeling, geological remote sensing, geostatistics, and the application of data science and UAVs in mineral exploration. So without further ado, I'll hand it over to Ehsan for his presentation. Yeah. There we go.
All good. Yeah, well, thank you everyone for joining us today. And well, I'm Ehsan, research associate in the Earthbite Group, University of Sydney. And well, today I'm going to talk about the use of machine learning in processing remote sensing data for in our exploration, actually, my presentation has two major parts. In the first part, I'm going to talk about some basic concepts of remote sensing and spatial data analysis, and then I'm going to provide you to speak about some practical examples of using machine learning for processing remote sensing data, and also generating different maps, including lithological maps, alteration maps, and also lineament maps using remote sensing data. Well, here you can see a standard definition and a formal definition of remote sensing data, but in simple words, I can say that remote sensing is the science of data acquisition from data acquisition and also determining the characteristics of objects and phenomena without contact. And there is a slight difference between photogrammetry and remote sensing. Actually, in photogrammetry, we try to specify the coordinates of the objects and phenomena based on the images that we have. But in remote sensing, actually, we are provided by some images that actually are based on the digital number values and also the physical characteristics of objects. And they provide some information about lights and colors. And remote sensing platforms are majorly divided into two types, actually, the active and passive platforms. And in active platform, actually the source of the energy and also the recorder are the same. And the sensor itself, or the platform that sensor has been mounted on, is also the source of the energy, like what we have in the case of the radar data. And in passive platform, actually the source of energy is the sun, and the sensor only records the radiation that it receives from the ground surface. And here in these figures, actually, in the upper figure, you can see the passive platform. And you see that the source of energy here is the sun, and the sensor only records the radiation that it receives from the ground surface, and then it is transmitted to a ground station.
Hi, sorry to stop you. I think the audio, they can't see you because you're not in the camera.
Yes, here is okay.
Yeah, I want to sit. And there's a problem with the presenter view as well. We need to make sure. Yeah, they just messaged me saying that it's yeah, please change. You can't see me.
Hi, Bhavik. We can see the slides, but it's in presenter view.
You can see it in presenter view. Okay.
Correct. Yeah.
Because they want to see that screen, but the screen should be mirrored. Okay. Let's go here.
Hide presenter view.
Hide presenter view. Okay. Can you see that?
Yes, that's better. We can just see the one screen now.
Yeah.
Thank you.
Sorry about that.
Yeah, and in the case of the active platforms, the source, as you see, the source of energy and also the sensor, they're all on one platform. And then the data is transmitted again to the ground station. Also, we can divide the remote sensing data into optical and radar datasets. And today I'm mostly going to talk about optical datasets and how to process these data types. And optical datasets, they are actually related to the visible and infrared range of the electromagnetic spectrum, while the radar datasets are related to the microwave range of the electromagnetic spectrum. And there are a few criteria that based on them we can evaluate the quality of remote sensing data types, and 4 different resolutions are defined. The first one is a spatial resolution. That actually the spatial resolution tells us that it tells us about the ability of sensor to distinguish two neighboring structures as separate. And for example, if the spatial resolution of a sensor is 30 meters, for example, it tells us that each pixel in that image represents 30 meter by 30 meter on the ground surface. And the DN value or digital number value or the pixel value that we have, it represents the average response that their sensor gets at that area. And it is obvious that we are interested in the lower cell size and higher spatial resolutions. And the other criteria that we have is spectral resolution that actually tells us the number of spectral bands in our data set. And it is obvious that we are we are interested in fine intervals of the electromagnetic spectrum, and we are interested in a higher number of spectral bands that enable us actually to distinguish between different structures and, for example, rock units, actually easily. And the other criteria is radiometric resolution, or it is also called bit depth, that we are interested, in higher bit depth or radiometric resolution, as it is obvious. And for example, in Landsat 7 data actually provides us 8 bit actually data, and the DN values are from 0 to 255. And the radiometric resolution actually tells us that how the sensor is able to distinguish different grayscale levels. And the other criteria is temporal resolution, that it tells us the amount of time that a sensor or platform needs to revisit a specific location on the Earth. And for example, in the case of Landsat 8, it is 16 days, that each 16 days it revisits a specific location on Earth, which is not that important in the case of our projects, since the time is not that critical for us. And remote sensing data are usually provided in digital format, and actually they are provided in images that are some sort of matrix, and we actually need to process these matrices that they include a path a specific number of rows and actually columns, and in each rows and columns we have the DN values, and we process actually these numbers. And the most basic actually processing method that we have is creating color images out of actually bands that we have. And we can easily create color images using different different combination of bands. And there are different systems like RGB, HSI, and others for creating color images. And among them, actually, RGB is the most famous one. And actually, the screen of computers, they are based on RGB format. And by putting the different spectral bands in the RGB channels, we can create different color images. And by actually, for example, in the right side, you can see different color composite images created using the Landsat TM data. That you can see that different features have been discriminated in these images, and there are different indices actually, like Sheffield index, optimum index factor, and others to determine the optimum actually combination of spectral bands for creating false color composite images. And here are actually introduce you some common remote sensing data types that we use in the geological mapping and also in mineral exploration. Well, since 1972, actually, there has been at least one Landsat, a satellite that was in orbit and taking images from the surface of Earth. And in September 2021, Landsat 9, the latest version of that, was launched, and now its data is available actually on the USGS Earth Explorer platform. Actually, from Landsat 1 to Landsat 9, the spectral and the spatial resolution have continuously improved. And for example, in Landsat 1 only had 3 spectral bands, and in Landsat 8 we have 11 spectral bands. And also the spatial resolution of Landsat 8 is now 15 meters that can provide us with accurate geological maps. Here you can actually see a comparison between Landsat 7 and Landsat 8 spectral bands. And you can see that, for example, in the case of the thermal bands, the number of thermal bands has increased to 2 in Landsat 8 compared to Landsat 7. And also, as you can see in the case of in the SWR region, actually, which is between 1400 to 1900, we have a finer actually band in there, which helps us actually to discriminate clay minerals in that region. And here are the grayscale images of different spectral bands of Landsat 7. And each of these bands actually provides us a specific feature that later we can use in machine learning and to train our images using the ground truth data that we have. Another common data set that we use in mineral exploration and geological mapping is ASTER data, which is only one of the sensors which we mounted on Terra platform, which was launched in 1999. And here is an image of this platform. And as you see, ASTER is only one of them. And actually, ASTER provides 3 different types of data. One is in the range of visible and near infrared. The other one is in the range of shortwave infrared. And the other one is in the range of thermal infrared. And the interesting thing about ASTER is that we have 6 spectral bands in the SWIR region, which is a very important region or portion of the electromagnetic spectrum for us, since it enables us to discriminate between different geological features, such as clay minerals, which is the indicator minerals of argillic alteration, or even indicator minerals of propylitic alteration or phyllic alteration. Here you can see the spectral bands of the ASTER data, and you see that the bands number 4 to 9 are located in the SWIR region, which is very important to us. And also we have 5 different thermal bands, band number 10 to 14, that enable us to actually create prospective maps for silicification and silica minerals. And these actually, the Landsat and ASTER data are known as multispectral data sets. And EO1, actually the Earth Observing 1, is a platform that on which actually they have mounted Hyperion and ALI sensors. Hyperion is a hyperspectral actually sensor, which provides over 100 actually spectral bands. And ALI is a multispectral sensor again. Hyperion data provides 220 spectral bands, and in the range of 0.43 to 2.4. And the spatial resolution of that is 30 meters. But ALI, as I said, is another multispectral data set, which is similar to Landsat data. And here you can see the difference between a multispectral dataset and the hyperspectral dataset. You can see the highest, actually the number of spectral bands we have in Hyperion data are much higher than multispectral datasets like ASTER and Landsat 7. And it enables us actually to discriminate different minerals, not only rock types or alteration zones. Also, it depends on the spatial resolution that we have, but this is actually a good characteristic of the data that enable us to discriminate between different minerals and actually provide the user with the maps of different minerals, such as kaolinite, which is the indicator minerals of argillic alteration zone. Actually, from now in the following slides, I'm going to review some examples of using machine learning for processing remote sensing data and providing different maps. And in recently, actually, we published a paper on actually a review of machine learning methods for processing remote sensing data in mineral exploration. And in this figure, you can see a diagram that shows here we actually classified remote sensing data sets based on the platform by which actually we acquire the data, the satellite data, airborne data, and ground-based data. And the features that you can actually map using the remote sensing data include lithological units, alteration zones, tectonic structures, and indicator minerals of different zones. And using the machine learning methods, we try to actually find out the relationship between the spectral continuum and also the our target features that enable us to create a really reliable evidential layer to be later integrated with other data types like geochemical and other geophysical data sets. And there are different categorization or classifications for machine learning data, machine learning methods. Here we have classified machine learning methods to dimensional reduction methods, classification, clustering, regression analysis, and deep learning. In dimensional reduction methods, actually, they transform correlated features to uncorrelated and independent features, which is the precondition of most of the machine learning methods. And here you can see three of them, which are the most famous one: principal component analysis, independent component analysis, and minimum noise fraction, which are, I can say that dimensional reduction methods are from the most popular machine learning methods that have been used for processing remote sensing data. And classification methods is actually a category of the unsupervised machine learning methods, in which actually in these methods we need a training data set to enable us to map our target features. And clustering methods are a subclass of unsupervised machine learning methods. They actually do not need a training data set to be trained, and they are only based on the characteristics of the data itself. And the other data, actually machine learning methods are regression analysis. Regression analysis, they're a kind of predictor, and they try to predict the characteristics of the data based on the features that they have in hand. And I can, for example, in mineral perspective mapping, there are lots of papers on using logistic regression analysis to predict the location of minerals. And the last category is deep learning, which is actually most of the deep learning methods, or I can say all of them, are based on the neural networks. And they can process complicated and large data sets. And they're a good option for processing hyperspectral data, where we have a higher number of spectral bands, and also when actually the spatial resolution is lower. And in those cases, we face a large amount of data, and we need more complicated machine learning methods to process them. And by combining actually the remote sensing data and by combining the remote sensing data, also machine learning methods, and creating a training data sets of our target features, we can create different maps, including lithological maps, alteration map, structural map, and even mineral map, based on the data set that we use. In another study, we proposed a computer vision-based framework for extracting tectonic lineaments using optical remote sensing data. And in this framework, we, that you can see on the left side, we applied different methods on Landsat 8 data, including we first started with applying dimensional reduction methods, PCA, ICA, and MNF. And at the end, even we compared the results. And also we applied some ancillary processing methods for reducing the noise of the data and also smoothing the images, like adaptive filter and median filter. And also we compared two different convolutional filter called directional and Laplacian as well. And edge detection and linear line extraction, these two are the main parts of this framework. First, we detect the edges, and then we try to actually create lines using those edges. And those lines can actually represent the faults, dikes, or faults in our study area. And we even used the digital elevation model to discriminate the extremes from other lineaments and to remove them actually from our lineament map. And on the right side, you can see our study area, which is Yenutera in the Gascoyne province in Western Australia. And you can also see in the right side the lineament map, which has been provided by the Geological Survey of Western Australia. And we are going to, at the last, we compared our results with the map that we have in hand here. Here you can see on the left side the result of our framework, applying our framework to Landsat 8 data. On the left side, you can see the result of applying the directional filter. And on the right side, you can see the result of applying Laplacian filter. And you can see it is obvious that the number of lineaments that we have extracted using the directional filter is much higher compared to Laplacian filter. But we concluded that the lineaments obtained by the Laplacian filter, they are more correlated with the geological, the result that with the map of the Geological Survey of Western Australia. But the lineaments we extracted using the directional filter, they were more correlated with the hydrothermal mineralization in the study area. And here are the density maps of these lineaments. As you can see in the upper right figure, actually, you can see that our hydrothermal mineral occurrences, they are more correlated with the high dense, actually more with dense areas. And in the bottom, you can see the maps that have been created have been published by the Geological Survey of Western Australia. And you can see that the Laplacian filter result of applying a Laplacian filter is also more correlated with the map published by the Geological Survey of Western Australia. And here is the diagram we used to validate our results, and we actually plotted the known hydrothermal mineral occurrences against the fuzzy score of the density maps. And the area under curve actually shows the amount, the accuracy of our maps and also their correlation with the hydrothermal mineralization in the study area. And as you see, the directional filter shows a higher correlation. And in another study, we integrated different selective dimensionality reduction methods to actually map hydrothermal alteration zones using ASTER data. And we applied this method to a region in Iran, actually in central Iran, to map alteration zones related to epithermal copper gold mineralization in that region. And here in these plots, you can see that in the left side, these are actually the graphs that we can actually see in the spectral libraries. And these graphs are generated using the spectrometers in the labs. But the sensors that we have up there in the orbit, they do not have such spectral resolution. So we need to resample these data. And in the middle column, you can see that we have resampled these graphs to the ASTER spectral bands. And in the right column, we have in the x-axis, you can see the number of bands actually. That here we have only considered the VNIR and SWIR spectral bands, which are 9 bands. And we have removed TAIR or thermal infrared bands from our study since they do not that much variation in the case of our alteration zones. And we selected those bands that show a high reflectance and also absorption as the input bands to the dimensional reduction methods, including PCA, principal component analysis, ICA, independent component analysis, and MNF, minimum noise fraction. And then we selected those components that are more correlated with the mineralization in the study area, and then integrated them, and using the fuzzy gamma operator. And on the right side, you can see the prospectivity maps created using the remote sensing data. And we classified our map using the fractal CA method, or concentration area method, and determined the certain anomaly values, which are shown in red color, and also the probable anomaly values in yellow color, and the background values that we have in blue. And in the upper right figure, you can see the another classified map of the study area. And you can see the mineral occurrences draped over the maps here. And using this graph, we validated our results. And here is a PA plot, prediction area plot, that tells us that we were able to predict 70% of the mineral occurrences in our study area and only 30% of the whole total study area. And in our latest paper, we compared the two conventional machine learning methods, including support vector machine and multi-layer perceptron, with novel with the recently developed method called convolutional neural networks for creating a lithological map of our study area. Here is our study area in the southeast of Iran, and you can see a false color composite image of our study area, which has been created using the Sentinel-2 data. And on the right side, you can see our training data set. Actually, these colored polygons, they have been drawn based on the field observations. And we have used this polygon to train our network and also other machine learning methods. And the interesting thing about convolutional neural networks is that in contrast to other machine learning methods, for example, multi-layer perceptron and also support vector machine, that they only consider a row of data. They're based on kernels, and they actually consider the spatial correlation between the features as well. And for example, if we have granite in a specific pixel, so it is much probable that we find granite in the neighboring pixels of that specific pixels. And that is why that you can see later that we got very good results using the convolutional neural networks for providing a lithological map. And here are the results. And you can see we applied these three different methods, support vector machine, multi-layer perceptron, and convolutional neural networks, to three different data sets: Sentinel-2, Aster, and also OLI, which is a sensor which has been mounted on Landsat 8. And we were able to create a map, a lithological map of the study area that includes 9 different rock units. And we validated our results using the ROC curves. And based on the results, the combination of Aster and convolutional neural networks, they showed a very high accuracy. We actually proposed this combination for creating lithological maps. And to summarize, actually, I can say that remote sensing data sets have provided a new data source actually to overcome problems associated with mapping geological features from field data alone, and they can help us to provide more accurate lithological and alteration maps and even mineral maps. And as a data-driven classification and prediction tool, neural networks have been widely used for processing remote sensing data and also creating mineral perspective maps or even alteration or lithological maps. And recent advances in deep learning methods, they have the potential actually to deal with large and complex remote sensing data, such as hyperspectral data, and with features in processing spectral and ground truth measurements against noise and uncertainties. Also, the limitations of different machine learning methods can be considered as obstacles to exploration geologists, and also the black box nature of them is also can prevent exploration geologists to use them in their projects, which is a problem that needs to be addressed later. And in general, using the advanced analytics methods in mineral exploration, we can provide more accurate prospectivity maps, and also it can help to achieve the goals that we have in terms of the sustainable development of in the mining industry. And our recent papers that I mentioned, most of them are associated with some open source and Jupyter notebooks, and you can find the link in the papers. And if you have any problems in running those notebooks and even running the Python codes, you can contact me via the email you can see here. And thank you all for listening.